Hello, welcome back to another lecture on operating systems, creating a simple operating system from scratch. Okay, yeah, so what did we look at last time? Last time I looked at creating some functions for printing hex values from memory on registers or wherever. And what else did I do? I think so I did a search through BIOS looking for interesting strings just to show really how you can write a little function in assembly to do stuff. And anyway, what I'm going to do now is, if you think about where we've come so far, so we started by learning how to boot, how to write some bootable code that when the computer started it would boot our code into a very primitive 16-bit mode, 16-bit real mode, and then we can start to play around with using BIOS and interrupts and things like that. But what we've got so far, and I'll demonstrate these things, not just say them, but we'll do some little experiments to confirm these things. But what happens is that BIOS loaded only 512 bytes for our boot sector from the disk. And if we wanted to write an operating system, then we need more than 512 bytes in memory. So we need to figure out how we can load some more data from the disk. And I'm gonna do that today, so that's what I'm going to look at. Yeah, as ever, BIOS can help us with this. BIOS has already loaded us from the disk, so it knows how to load stuff from the disk, and it can offer us some functions that we can use, just like when I printed a character to the screen using a certain BIOS interrupt and service request in one of the registers. Then I can do the same for reading from the disk. So I'm going to look at that. Now, with all these things, and the way BIOS is, I showed in the last lecture that when I ran the same code on VirtualBox and the same code on QEMU, CPU emulator, that they look to have different BIOSes just by the strings that we saw inside the BIOS code. And the point is that it doesn't matter if the BIOS is different, as long as the way that we can interface with the BIOS is consistent and backward compatible, then we can take any computer, any like x86 machine, and we should know how we can read data from the disk. Yeah. Now this is usually it only gives us basic control of the hardware usually, and often, like modern operating systems, will just bypass all of this BIOS stuff anyway, and we'll see that they have to later on when we look at 32-bit mode, when BIOS becomes unavailable. And but we need to bootstrap our operating system, so by using BIOS we can do that. Okay then, so let's just have a play around of it really. Then I'll build it up as I did before, and I'll just reference some stuff on the web, so you can see how I can do that. So let's have a look at my code. So what's my code doing here? This is just pretty much my basic code that I've built up over the other lectures that you've seen already. So I set up my stack. You'll see I set it quite high here, and I'll explain why in a minute, well, later on. And then I jump into this loop and I hang at the end. But down here you see I've got this include, which, if you remember, just means that I just include a load of other assembly code at this point in my file. And then I pad out until it's to make sure it's 512 bytes long, and make sure I put the magic number at the end so that BIOS sees us as a bootable sector on a disk, so a bootable disk. If I just look at my functions, if I go into there, you'll see I've just got the print string function that I created in the other lecture, and the print hex function. Both these functions are very useful, so it's good to keep things around that you've done already. But I'll close that for now. We don't need to look at that anymore. But I'll just be probably using those. Okay, so if we're doing something like this, we want to load some stuff from the disk into memory. We know that our boot sector is already in memory. We've already played around with that. We've verified that. We want to load some more data into memory. So it's always good to build things up like this so that you can verify what's happening at the moment. So what I'm going to just demonstrate now is that if I create this message, if I just call my message, call it, and I say db, I don't know, am I loaded in memory yet? Okay, so what I'm going to do is I'm just going to print this message on the screen using my print string function. So if you remember, all I need to do is move the address of that message that's in memory into the SI register, which is just a general purpose register for often used for referencing strings. But really I could use any register, but this is what my print string function uses. So into SI I'm going to put the address of my message. So I just used a label, which is the easiest way to make sure it uses the right address. And then I'm going to call print string. And that's run our code. Okay, so I've run my boot sector in my CPU emulator, and it's showing my string. Am I loaded into memory? So that string must have been loaded into memory because it's not on the disk. Well, I mean it's on the disk, but it's also been loaded from the disk into memory because the CPU is able to print it, and the CPU can't just directly execute or use data from the disk. The data has to be loaded into memory, just like my boot sector is loaded in from the disk by BIOS into memory and then executed. So that string that I just put there is definitely in memory because I've just printed it. So that's good to know. Now, if I just close this window, sometimes QEMU locks your mouse out, so because you can use your mouse as inside the emulator. Anyway, so I printed that message. Now if I look here, because I'm doing the padding out after my message, this message is actually inside my boot sector, so within the 512 bytes that I'd expect BIOS to load. I can also, it's always good to confirm things. If I do ghex, where is it? So this is my boot sector, and these are all the bytes in it. So this is what actually gets written to my into the file that gets used as QEMU interprets my file, my binary file that I create with my assembler, as though it was a hard disk. It's just how it emulates it, so it does it realistically like that. So this is the first sector that will be written to the hard disk, and if you look at it, it's 512 bytes long, and you can see that my string is in there. So when this does get loaded into memory by BIOS, my string will be at an offset from the start of wherever it was loaded to, and you remember it was 7C00, which is where BIOS always loads us. So this string's in my boot sector, and it gets loaded into memory because BIOS loads my boot sector. Okay, it's important to know that. Now what I'm going to do is just take this string and put it after all of my padding. And now what this should do is, well, when I do this padding code here to pad out my boot sector with zeros so that I can get my magic number as the last 2 bytes of that boot sector, then it means that my message now, these bytes here for my string, must be after my boot sector. So they must be in the bytes following the first 512 bytes, the first sector on the disk. What that really means is that when I come to now try and print this message in my boot sector code, it shouldn't be able to print it because BIOS won't have actually loaded this sector, the second sector from the disk. It would have only loaded the first one. So this thing will never get loaded into memory. Let's just confirm that. First of all, let's look at let's compile it first. Okay, well it's not printing my message, which is what I expected. Let me just check that the binary, how that looks. Well, you see here, this is the end of my boot sector, 512 bytes. There's a magic number, and this is where my string starts after that. And yeah, it's not been loaded by BIOS because it fell outside the size of the boot sector. And what this means then is that if we do want to load any more data, into memory, we have to bootstrap it. So we have to get our boot sector code, so that code that is in that first sector, to then load some more data from the disk. And then with a kernel, what you would do is you would load your kernel, and then you jump to the main function of that kernel, which would then start probably doing some more bootstrapping. So it might load some drivers, and it might load a file system even, which is a a more high level abstraction of the disk, and then using the file system it might find other files, maybe driver files or modules, and load those. So it's all, we bootstrap it up like this, we gradually increase, we pull things into memory and then execute them, but you have to do it bit by bit because BIOS only loads at 512 bytes. So let's have a play. So the goal then now is, if I want to demonstrate how we can also load more data from the disk, then my goal, a good goal, is for me to be able to print this message like I just tried to then. So if I can load this second sector, so the one after the boot sector, into memory, and if I can load it after, straight after to where my boot sector is loaded into memory, then this code that I've got here, this exact code, should print the message to the screen because it will then be in memory because I loaded it. Okay, let's have a play. So we need to, how do we load stuff then? Well, first of all, we're going to create some more functions now. Well, we're going to create one function that loads some more sectors from a disk. Now, I come to this page now. So I'm just looking on Wikipedia. Seems that people tend to fill it up with useful stuff like this. But if you were writing an operating system, then just like when you're writing code for, when you're writing like user space programs in an operating system, you look at APIs and things, you look at, you know, what functions can you call, what libraries are there. But at this very low level, what we want to do is understand what services are available in BIOS for us to use to boot our operating system or to do any other hardware stuff. So we need to look at, so at our level, at our low level, we're interested in the interface to BIOS. Just like when we printed that character to the screen, I just told you this, we know we use this interrupt and we use this setting in the AX register to print a character. And now we're going to look for the BIOS stuff that does disk stuff. Now, BIOS allocates interrupt 13 for all these different functions relating to using the disk drives, right? And they could be floppy drives or hard disk drives, and it kind of abstracts them so that you don't need to worry about what they are. Usually you just refer to them by an ID, so a drive number 1, drive number 2, and then you can read data from it. In practice, I think I probably mentioned before, but if you did have like a certain kind of drive, like a floppy drive, although we don't see too many floppy drives now, but still we do get plenty of other different devices. Then for a floppy drive, for example, when you want to read data from a floppy drive, the first thing you have to do is switch the motor on and leave it for a few milliseconds or seconds to spin up, and then you can start asking the hardware to read data or write data. And you know, you've got to, the hardware controller can do very specific things for that hardware. So with a floppy drive also, you wouldn't want to leave the motor running when it's not reading from the disk. So use the drivers for things like floppy drives. After so long of inactivity, they'll switch the motor off because otherwise the motors wear out. So you can see that the difference, although at an abstract level we're just storing data on it and reading data from it, and it's got some maximum capacity, it's usually very specific how you control it. And I guess you could say the same for anything like for a CD writer, for example, where it burns the disk and stuff like that. You have to make consideration to how it actually works. But the point here is that BIOS has created some abstractions for us, so we can just tell it, we can ask it to read data for us. So we're using these things. Now you can have a look at this. So if you look for interrupt 13 on Wikipedia, you can look for other stuff, just search for BIOS if you're interested in other functions. But all of the interrupts are listed, and all of the register settings to access certain functions within those interrupts are all available for you to look at. And this is what, when people were writing, like, you know, the operating systems that we have today, when they started writing those, they would have been reading this stuff along with the CPU manuals to figure out how to, you know, what they can do with the hardware. Okay, right, let's get on anyway. Too much digression as ever. Right, so what we want is this one here. So if we call interrupt 13 after we've set the AX register, so the high byte of the AX register, to hexadecimal 2, which is also 2 binary, 2 decimal, then this will select the read sectors from drive function that we can use to read some sectors from drive. So that's what we want to do. But what we find is that it's not quite so straightforward as when we printed a character, because we've got a few other parameters for it. So here we see if we want to read a sector from a disk, we've got to somehow give some, you can think of it as coordinates or directions. You know, like if you were trying to direct somebody to your house, then you tell them like what town you lived in and what street. Well, it's the same with a disk. The disk, I've got a diagram actually. Let's show you a diagram. Here we go. So a hard disk, a typical hard disk looks something like this. If you take the case off, if you do take the case off like this, then you can't really use it again, because as soon as you get dust inside your hard disk, the dust particles are ginormous compared to the space where you write data, so it's going to kill it. But anyway, here's a picture that someone's kindly done for us already. They've already ruined their hard disk. And if you look on here, what you actually have is you have these sort of surfaces, these platters, and they spin around underneath this this arm of read-write heads, and it looks basically like a record player, and it works in a very similar way, in that on this disk surface you can magnetize areas using this head, so you can change the magnetism of it, and by doing that, it means you can set a state on it that can then be, when we turn it off and then turn it back on, we can still see that there's some state there, that some area was magnetized or not. And you can imagine that you could set 1s and 0s on there based on magnetism. Anyway, so we can do that with this thing. But what it means is that if we want to access a particular area of this space, then we need some way of addressing it, and we can do it like this. It basically just derives from the way it works mechanically. So you can see that this arm here can move in and out, so it can seek in and out like here. So that's one coordinate, and the way we specify that is we call it the track or the cylinder. So it's the particular, I suppose it's the concentric circle that you can imagine that the head is currently resting on, and if this moved out here, then it would be our cylinder. It's also called a track, and you can maybe think of it as like a running track. So if somebody was running around one of the tracks, something like that. But also what we have is we've got stacks of these things like here. So they're not just one of these services, they often stack up just to give us more capacity. And all of these arms sort of move in together. And so not only can we index a track or a cylinder of this, we can say which head we want to use. So there'll be a head on the top of the surface and a head underneath the surface, because it's two-sided. We can magnetize the top or the bottom separately. So that's what we've got really. So we've got, the way we can register it is the cylinder, so the track as it's called, that goes around it, and then which head, so which particular surface of all these stacked up platters that we want to reference, and then on that particular track, so if you can see a track going around here, we can index a particular sector that we want to read. So this is important for this BIOS function that I'm going to show you, because even though if I take, I think I've probably got one here. So here I've got just a USB stick. Okay, now I could read and write sectors on here, but this doesn't have the same physical structure as a hard disk. But even with BIOS, if I plug this in, I should be able to. Well, it depends. I've not tried that. It's possible. But you might have some other piece of hardware that doesn't have that same layout. But BIOS sort of has a legacy interface that reflects disks how they were when the computer was first. You know, the x86 was first designed, and the hardware that went with it. Anyway, basically we need to understand this. There are other ways of addressing sectors on a disk, but this is the one that we're going to use. Right. So we need to understand that. So the cylinder, the head and the sector, so it's often called CHS, it's often referred to, and that's how we index a particular sector on the disk. Okay, let's go back to our stuff now. So now we understand that there are, if we set these certain registers before we call that interrupt 13, then it's telling BIOS what to do. We're giving it some parameters of what to do, how to read from the disk, where to read from. And so there's this one here, AL, which is we put in there the number of sectors that we want to read. Okay, that's from we first give it a starting point, and then we tell it how many to read from that starting point. So CX it will be the this will mark out the track or the cylinder and the sector. So in the high byte and the low byte, it's divided between those. DH will tell us which read-write head to use. So that will select the particular surface of the stack of disks. And then DL tells BIOS which drive to use, because we might have several hard disks and we might have a floppy drive in there or something like that. And also we've got this ES, so this general purpose segment register, which we used when I was doing when I was doing the BIOS searching thing in the last lecture. And BX is the address, 16-bit address that is modified by this sector. Anyway, this is basically, we set these registers to tell BIOS where to read, when it reads the data from the disk, where to store that into memory. So we tell it where to store it, basically. So let's have a play. And when we return from the BIOS interrupt, after we've done this stuff, after BIOS has done it for us, read the data, it will set some other registers to indicate what happened, whether there was an error or not, because the drive might be broken, or we might have put some bad input in there, so it gives us some error feedback, which is very useful at this low level, because it's quite nice to have some feedback, because often you don't get much. Okay, so okay, right, I'm going to write some code now. So I want to write a function that loads some data from the disk. What I'm going to do is try and load this this second segment that wasn't loaded by BIOS into memory immediately after my boot sector that was already loaded, and then this code should work. It should print that message. So let's just do that. So we're going to define a function down here, and we're going to call it read from disk. Now, what do we need to put in here? So, well, we can start from the interrupt. So at some point we're going to call interrupt 13. Okay. Now if I just do that now, it's not going to really work. The other thing I want to do before I call this print my message, I need to read from the disk. So I'm going to do something like this. Call read from the disk. And then when I try to print the message, it should work because it's loaded the stuff into memory. Right. So I need to set up the parameters now for that read memory BIOS call. So that's what I'm going to do. So let's just have a look. I'll just switch back and forwards with them. So, well, I've got AH, let's say that. So AH move AH, and it was OX. Is that right? Yeah. Okay, sometimes you'll see hexadecimal notated with an H like that, or sometimes like a 0x. As long as you do it consistently, it doesn't matter. Right, so I'm going to store that in. So what this means is, if I just refer to here, is this by setting AH to this, it's basically selecting this BIOS function. So I might as well use this as my comment. Okay. So now what else have I got to do? I've got to find, right, the number of sectors to read, AL. Now, what I can do is, well, for now I'll put this in, but if I wanted to, I could expose that as like a parameter to my function almost, so that I don't set that within my function, but I let whoever set it before they call my function to the number of sectors they want to read. But I'll put it in here for now, it doesn't matter. I'm just going to say move AL, I think it was AL sectors to read, so the number to read. I'm just going to read one sector. I'm just interested in reading this one sector after my boot sector from the disk. So the second sector on the disk. So let's set this to 1. CX, so CH and C CL will be the track and the sector. So if I do cylinder head sector, if I think about it in that way. So if I do move CH, now this is the cylinder number, and if I just check my notes, just the cylinder number, when we reference that in BIOS, it's the first cylinder is cylinder 0, and it's cylinder 0 where our boot sector will be on that cylinder, and I don't know whether that's in here or out here. I guess that's a matter of the hardware, but basically we're saying select cylinder 0, so the first cylinder on the disk. Okay, now we want to set the cylinder. Let me just write that in. So this is the number of sectors to read. It's very good to comment your assembly code. It's easy to forget it when you dip in and out of assembly. You think, what did I do that for? So you might as well make life easy for you. So this is select first cylinder. Cylinders are also called tracks. And then the next one, so we want to select the head. So the cylinder is you can imagine the circle going through all of the stack of the discs, and the head will select a particular surface, whether on the top of a cylinder or underneath one, and then is for each of the cylinders that are in the disc. So I'm going to say, for each of the surfaces, the platters. So I'm going to say select the first head. Okay. Now let me just check my notes with that. Yes, so the first head is also 0 base. So the first head is going to be so let's move DH, which is where the head goes, and the first one is 0. Select first read write head. Okay, and lastly we'll set the sector. So which sector do we want? Well, the first sector of the first cylinder of the first head is the boot sector on the disk. Okay, and what we want to load is the second sector after the boot sector. So that will be like I've got here, it will be the first cylinder, which is cylinder 0. It will be the first read write head, which is read write head 0, because it's 0 index. But a bit confusingly, the sectors in BIOS, the first one is number 1, so to read the second sector I put 2. So although all those other ones are 0 based as the first one, the sector that we select, the first one is number 1 and the second one is number 2. Okay, so you often find these things, and you basically not got to make too many assumptions, otherwise your code ends up not working and you wonder why. So you just got to read the documentation and search around. Anyway, so we need to select the sector. So the sector goes in CL, okay, because this is just showing that it's a low byte of the CX register. So move CL. Remember, 1 is the first sector, which will be the boot sector, but we want to load the second sector after the boot sector, which is where this message should be, because it aligns just after the first sector here. Okay, so select second sector. Right, what else do we need to set? So we've told it which cylinder to select, and we've told it which read write head to select. So this one, or this one, or this one, or this one, or the ones underneath, you can't see them on here. And we've told it which sector to read, which is the second sector. And now what we've got to tell it is where to read that data to into memory. We've also told it how many to read, and we told it to read 1 sector, starting from that address that we gave it, that cylinder head sector address. So we need to set ES and BX. Now what I'm going to do is, if you remember, I can't just set ES like this. I can't just set it like that. If I could type properly. What I've got to do is set it inside another register first. So if I do move BX 0, move ES BX. That will set the ES segment register to 0. And all it means is that we're not using segmenting. We're not applying the segment modification to the 16-bit address in BX. And we're not going to load it higher than this. We can set that segment if we want to load it somewhere else, but which in practice we would do, but we're not doing that now. Just to simplify the example, really. So we've set ES to 0, so I can just write a comment here so I know. So ES goes to 0. And where do we want it to write to? Well, I'll do it in decimal because it might be easy. Yeah, it'll be easy to understand without thinking about it in hexadecimal. But if I'll use BX. We need BX, so it's ES. So BX is the 16-bit address, and ES is the segment address that this BIOS function looks at to see where we want to write that data from that's read from the disk. So in here I'm going to put, well, if I put 7C00, which I can play around with these things, or you can if you want to, that will overwrite my boot sector because my boot sector is loaded at 7C00. I want to write it to the next 512 bytes after my boot sector, so it follows on seamlessly as though BIOS loaded both those sectors consecutively. I mean, yeah, one after the other to memory. Although it didn't, because we saw that it only loads the first one, but we're loading the second one. We're bootstrapping up our extra stuff. So the address we want is, well, I can write it like this. I can say OX7C00, which is where BIOS loads us, plus 512. If I wanted to write that in hex, it would be like this, because 512 is 200 in hex. But let's write it like this so it's clear. So we're saying we want to load it to this address plus one sector's number of bytes. So it should then load it straight after. So let's see what happens now. Let's just double check what we've done. So it's always good. It's easy to make mistakes, as you've probably seen me doing the other things. But we don't worry too much about that stuff. As long as you understand what you're doing and how to figure out things, that's the more important thing. Everybody makes mistakes. And this sort of stuff is not really for memorising. You know, you can memorise. You can use your memory for more important things and interesting things than this. Anyway, so we set AH to this number 2, and all that means is it's when we do call interrupt 13, BIOS is going to look at the AH register, decide which sub-function to call within that interrupt, which service, and this one selects read sectors from drive. And there are other functions like write sectors to disk, or format the disk or something like that. But this is the one we want. So then what we do is we set the number of sectors we want to read in this register, and then we select the cylinder we want, which is the first cylinder, or track as it's often called, and then here we select the first read-write head on the disk, and then here we select the second sector on that head on that cylinder, and the second is the sector after our boot sector on the disk, because BIOS has already loaded our boot sector. And then what do? We tell it where we want to write it to in memory, so we just give it an address, and here basically I've just set ES to 0, so it doesn't do any segment transformation, and it's just going to write it to 7C00 plus this, so one sector's worth of data above my boot sector, so it should immediately follow it in memory. If I look at my this diagram that I often show you, which is always useful to think about in memory, then it's going to load, this is my boot sector, and I'm going to load it, my extra sector, just straight after it, so we can start executing like this. Okay. Right. Note when I say after it as well, this might be confusing at first. I suppose you take it for granted after a while, but see this, sometimes you see memory upside, well, depends how you think about it, but here 0, the lowest memory address is down here and the highest one is up here. And so when I say I'm loading my, when I say I'm loading it after my boot sector, I mean I'm loading it here, which is higher in memory, okay? Because we execute like this way, okay? We execute when you run instructions. the CPU executes the instruction, then it moves to the next one above. So always make sure you know which way around the memory's going when you look in a diagram like this. Okay, so we've told it where to write it to, so let's see if that works. Let's just have a look. Okay, well, it's not printing my message, so that means that it's, well, I could assume it's not loaded it there, because if it had, it would have printed it. So something went wrong with that BIOS function. And if I want to know what went wrong, then I need to really look at the how it feeds back what happens. So I've called the interrupt there, but I don't do any checking to see what registers were set after it happened. So one thing I can do is, if I look at this, and this is all the input that it takes, the parameters that it takes, and these are the output parameters. So one thing, a simple one I can check, is that it says if BIOS has an error reading from the disk, it will set the carry flag. I might have mentioned before or not, I don't know. Well, probably in the comparisons. So when you're doing control statements like if this, do that, then you do a comparison and then you do a jump, and the jump is based on the instruction that happened before, the outcome of it. And you have flag registers that CPU keeps its state on. So sometimes when something happens, like the carry flag, this CF, is just a particular bit of the flags register that gets set when a number is carried from like an addition or something like that, and you get overflow flags and flags like that. But all it means is that when this particular flag, this bit in a register, is set on an error condition by BIOS when it's reading the disk. So we can check this, and one instruction we can use for this is JC, which means jump if the carry flag is set. So what we can do is we'll put down here something like read error, and we'll have an error message, disk error, reading disk. Okay, and what we'll do is in this block here, I'll just move SI disk error, call print string, and then I'll just jump indefinitely. So if I come here, then I've made a mistake somewhere, and I just want to hang the CPU and print a message out, so at least I know what's going on. Now, I only want to jump to that bit of code if, sorry, what I should have on here as well is a return, so that when this function is called, we get back up here, otherwise it's not going to work at all. So, I've put that in now, so nobody noticed that one out. So we've done our interrupt, and now what we want to do is check the outcome of that last read that we did. So what I can do here is do a JC read error. Read error, and what this means is jump to error message if carry flag set, and it's BIOS that sets it when it's a mistake. So the carry flag is used for other things, but often you find at this level and with this kind of interfacing that a bit of code can respond in any number of ways, and it'll just use whichever way it wants to, and as long as you know what that way is, you can check and see what's going on. So let's see what happens now. So if I run this and BIOS set that carry flag, then I should get an error message displaying if I've not made it. I need to put something else I need to put on here is null zeros for my string. Luckily, when I did this, probably there were zeros there anyway, so that's why it didn't print stuff out. But I've just put my 0 on the end now. Right, let's just have a look. Okay, so there's no message there. Let me just check that I've done this correctly. So, well, one thing so this is a mistake that I didn't expect to make, but because I've got my message down here after my boot sector, without thinking about it, I've just added my error message after there as well. So my error message now is actually outside of my boot sector, and so it's so that I'm never going to see my message, and I'm never going to see my disk error message because it's not in my boot sector. The whole point of what I'm trying to do is to load that stuff that's not in my boot sector, and if my error message is not in my boot sector, then it's not going to be very useful. So here I put it inside the boot sector now, so it's inside this before it gets padded out, my first boot sector. So let's just try this. Do I get an error message? Good. Well, this is good, but it means there was a fault when I was reading that, using BIOS to read data from the disk, and now I've got an error message, so I've done something wrong. The good thing is that BIOS has told me there's an error, so I can try and figure out why now. A little bit frustratingly, as I found playing around with this stuff, was that QEMU, the way it seems to work is that if I don't pad out my second sector that I want to load, so that it's a full sector's worth of data, even if it's zeros, then it won't load it. And it's possible that it does that because when it emulates a disk, if it doesn't have a full, if the last sector isn't full, then maybe it just assumes, it rounds down, so it says that the disk capacity is, you know, only the number of full sectors worth of code or data that I used for the virtual disk. Anyway, what it means is that if I pad this out now, and an easy way to do that is I'll just do times, well, if I times it by 512, which is the sector size, then because this message is longer than that anyway, this should overflow into a third sector, but it means that this sector will be complete where this message is. I'll look at the hexadecimal again in a minute, just to show you that stuff. Just play around with these things. Always look at your hex code as well to see what was generated using ghex or something. But let's just see if this works now. If I've done that right. So I'm saying stick 512 zeros bytes on the end of my compiled code. There we go. So what's happened? We've done it, so we've loaded, so now it's printing that string. Am I loaded in memory yet? Because I've loaded it from memory. And we saw that if I didn't call my function, okay, so this is good, this is what we're trying to do here. If I didn't call this read from disk, and I just tried to print my message, which was down here, like we did before, then we see there's no message, so QEMU just tells us it's booting from the disk, and then we get nothing else. If I put my code in, read from disk, I get it, so I'm loading that second sector now. So this code is all working, that's very good. Yeah, let's just have a quick look at the hex as well, just to see what we've got here, just to really explain what's happening. Now, the way this QEMU works, it's an emulator, so it doesn't actually have a hard disk that it's using. It's just its hard disk is initialized from a file that I pass into it that just has raw bytes in it, and it basically treats that as a hard disk with sectors of 512 bytes long, and it's that BIOS is reading from. So BIOS, as far as it's concerned, is just the BIOS code in QEMU. It's probably just thinking that it's reading a disk, or it's made to behave like it is. So when I compile my assembly code, I compile that and it just generates a flat file with just, you know, continuous bytes that represent data or code, which is what I'm looking at now on here. And initially what I was doing was I was making it 512 bytes long, the size of a sector, and I was putting a magic number on the end of it. And that was all I needed to create bootable code then, to be booted by the thing. But now what I'm doing is I'm adding extra sectors onto the end of my file. I'm making my assembly generate a longer file. So QEMU just sees it as a disk with, you know, a sequence of sectors. But BIOS only loads the first one. So I have to use the BIOS function to read some extra segments from the disk. And I use the cylinder head sector addressing scheme to do that. And if I look at this raw code now, what I see is I've got, this is all of my code actually. It's only small actually if you look at all of these zeros that pad it out. to the magic number. So this is the end of the first sector. It's mostly zeros really. My code and data only makes up this from my boot sector. But then you see that because after I padded it out, I added some more stuff to my assembly code. If I just move this to the side, come back. Because after I padded it out down to here, which is what we see here, I just carried on my assembly code beyond that 512 bytes, and I just stuck my message here. So the offset of this, my message, from the start of my boot sector is 200. Yep. And so it's just the next sector in the disk, and then I just do this times by 512 to stick lots of zeros in the end. So then I just pad it out with zeros. And the reason I do that is because I mentioned that QEMU doesn't seem to load like a partial sector, so we just pad it out if we want it to be loaded. Otherwise we get an error message in BIOS saying that you can't read it, and you can spend a long time debugging that sort of stuff. Luckily I managed to figure it out. But there we go. So so what did we do? The most important things there were that not what we actually did, but how we did it. So it's always good to build it up gradually, what you're trying to do, to have a goal that you want to get, which was to print that message that wasn't in the boot sector. It would have been in another sector on the disk, and then load that. And if we could show we could do that, then we could show that the read function stuff is working. It's almost like very low-level test-driven development, I suppose, where you have a test, you have a goal in mind, and you develop your code until you meet that goal. So we did that. But the other thing was that I came to this page here. There were probably lots of other pages, but this was just a convenient one that I found, and it lists the stuff quite nicely. And this just tells me all of the different services that are available in BIOS for disk operations, yeah. So you can just look at these and it tells you how to set them, and if you look at particular ones it will tell you what registers to set, like to write sectors to a drive, which is good. There's one thing that I'm just thinking about, I just missed out, and that was, which you'll see that we in this case we succeed by a fluke really, but it's an interesting thing to talk about. When I call this read sector in the disk, I forgot to set the DL register, which is the drive to read, the drive number. Now the problem is I said the drive number is like an index, like 0, 1, 2, 3. Actually it's not like that. Usually it's, I think for the first hard disk it's usually 0x80, and you get different values, default values for like different kinds of drives, I think like floppy drives. But one thing that I've made advantage of here, just kind of without thinking about it really, is that when BIOS first loads, if I just comment this code, when BIOS first loads, it must use a similar function, or possibly the same function that we're using now, because if we check the DL register, or if we look in DX and look at the low byte, it's set to the drive that we booted from, and we can use that as a way to know which drive we want to pull more data from the same drive that we booted from. We can look at the value that BIOS already had in the DL register. It's like it loaded this and left it there. Whether it does it on purpose, I mean it probably does it on purpose, but you can imagine that it just left it there after it used this same function that we're doing. So what it means is that DL, the drive number, was already set when I called this function to the right drive that I booted from. And if I just do a print hex using my very useful print hex function of, if I do move, because my print hex function takes it takes 16-bit values, not just single bytes, then I'll just load DX into actually I just thought as well, the print hex function, another fluke really. There aren't many registers, so I guess my print hex function takes DX as the value to print the value of anyway. So if I just call it as soon as I've booted without changing DX, we should see the drive number in here. So here it's saying, so that would be DH, and this would be DL, and it's saying 80, which is right. This is what the first drive usually is. So yeah, so there you go. Now what we might want to do, if we were playing around with different drives, is that before we do anything in our boot sector, is that we just push the value of DX onto the stack. And it means that when DX is modified later on, we'll still, somewhere, we'll still be able to access the original drive that we booted from, if we've overwritten that DX value. Then we can set it down here in this function. I think that's it really. I've gone through all of those things. So what we have now then, building up on all of this stuff, is that we know how to load extra data from a disk. So the next thing we can do, although we're going to look at something else. We're almost there now really. Our goal is to just boot a kernel like compiled in C. From there you can start to build it up even further, but you move away really from the assembly stuff, and then it starts to be, looking more at how you can use devices and stuff like that. But we're at a stage now where we could, if we wanted to, we can compile something in C, which we'll do soon, stick it onto the end of our disk somewhere in another sector, and then in our assembly boot code, we have a little bootstrap bit of code similar to what I've got here, but that loads the sectors that contain the kernel somewhere into memory, somewhere that's free, that there's nothing else in, and then it jumps to it and then starts executing the kernel code. It might jump to the main function. If you had like a function called main, you would jump into that and start executing that code, and that would call other C functions, but then you would have booted it into a higher level language, which is nice. You can start to work much faster. So this is good now, so we can do this. So we're really progressing. We'll find that there's one annoying thing that we're going to do, is that we're going to next try and figure out how to switch our CPU from 16-bit compatibility mode into 32-bit mode, protected mode, which is what sort of modern operating systems would be using. Okay, now you see it's mostly 64-bit machines now that people are using, but 64-bit, I'm not going to look into that, switching to 64-bit mode. You can find information on it in the CPU manual, and on things like OSDev. It's quite a very good resource for that. But they're very similar. So 64-bit mode is like an extension of 32-bit mode really, where it widens the register values, and you get a few more things, but it's based around the same ideas. But anyway, we're going to look at switching to 32-bit mode, but then it gets a bit. It's not hard in itself, but it's just you have to really go over and over and over it until you understand it. But once we've done that, we can boot a 32-bit mode kernel, 32-bit compiled kernel. It makes it much easier when we're addressing memory rather than using these strange segment registers where you shift by 4 bits and add it. We get a much easier memory model. Okay, I'll stop talking about that stuff now. We'll look at that later. So we looked at reading from the disk, so I hope that was useful. Just have a play around, look at those wiki pages there. They're quite good at explaining things. Write some boot sector code. Just make sure you build it up. So don't expect to just copy some code from somewhere and it to work exactly as you'd expect it to, because it never does. Okay, right. Thank you very much.